Welcome friends to my YouTube channel. Now on my last lecture I shall discuss I completed the entropy chapter and from my today's lecture I will going to solve few numericals related to thermodynamics. Okay. So at first today I shall start from the first law. Okay. So numericals related to first law related to first law. Now in order to grow your concept it is necessary to do numericals of each chapter. So here we do few numericals. Okay, the first numerical is that a gas at 10 atmosphere pressure and 1 liter volume expands adiabatically to 2 atm and 3.16 liter volume. Okay, so that means here given the initial pressure, that is 10 atmosphere. At first you have to write down the quantities which are given. V, this is given 1 liter. Okay, the final pressure is also given 2 atmosphere. Okay, and the final volume, this is given 3.16 liter. So we have to find out what will be the amount of work done by the gas in joule. Okay, so amount of work done, we have to find out the amount of work done. Okay, here also given gamma, this equals to 1.4, that is here consider the gas to be diatomic. So fine, so it's very simple numerical formula. So what will be the amount of work done during adiabatic process, that we all know, that is P1 V1 minus P2 V2 by gamma minus 1. This is the direct formula of work done by a gas during adiabatic expansion. So just since they are given in same unit, you can substitute it. So what is my P1? 10. What is my V1? 1. And what is P2? That is 2. And what is V2? That is this. And what is gamma? 1.4. Okay, so if you calculate it, what will be the result? The result will be 9.2 joule. Okay, if you do it in calculator, the result will be 9.2 joule. Okay, so this is the amount of work done. Okay, so at first write down the formula P1 V1 minus P2 V2 by gamma minus 1, then substitute these values, you will get 9.2 joule. Okay, so this is the first numerical. I hope you will all understand. So at first write down the quantities that are given in the numerical. Okay, then use the formula. Okay, so it is necessary to know the formula. So this is the first numerical that I have done. Okay, so let us now move to another numerical. Okay, let us do another few numericals. Now the second numerical is that 1 mole of monatomic gas. Monatomic gas means gamma is 5/3. That is monatomic gas. Monatomic gas. At 27 degrees adiabatically compressed in a reversible process from an initial pressure of 1 atm to a final pressure of 50 atm. Okay, so initial temperature is given, that is 27 degrees Celsius, that means 300 Kelvin. Initial pressure is given, that is 1 atmosphere. Final pressure is also given, 50 atmosphere. So here we have to calculate the difference in temperature. Okay, so we have to find out the difference in temperature. Okay, so at first we have to find out the final temperature. Okay, so what formula we will use? I shall discuss the pressure, three adiabatic relations for a perfect gas, among which here we use the temperature pressure relation. Okay, that is, what would be the relation? That is T to the power gamma by P to the power gamma minus 1, this equals to constant. That relation we will use. Okay, that relation we will going to use. Okay, so T1 to the power gamma by P1 to the power gamma minus 1, this is equals to T2 to the power gamma by P2 to the power gamma minus 1. So you can simplify it. T1 upon T2 to the power gamma, this is equals to P1 by P2 to the power gamma minus 1. Okay, so substitute all the values. T1 is 300, so that is T2, and you put gamma 5 by 3, that is 1.66. P1 is given 1 and P2 is given 50, and 5 by 3 minus 1, that is 2 by 3. So if you calculate this in calculator, the value of T2 becomes this 1434 Kelvin. Okay, 1434 Kelvin. Okay, so this is the result. So we will get the final temperature, and what would be the temperature difference? That is simply T2 minus T1. So what will be my T2? 1434 minus 300. So this is 4 3, this is the result. So this is the temperature difference. Okay, so at first we find out the final temperature by using the pressure temperature relation, that is T to the power gamma by P to the power gamma minus 1 equal to constant. We substitute all the values and get T2, this is equals to this, and then what will be the temperature difference? T2 minus T1. Okay, so this is also a easy numerical, simple numerical. So let us move to another numerical. Okay, now the next numerical is that immediately on explosion of an atom bomb, the ball of fire produced has a radius of 100 meter at a temperature of 10 to the power 5 Kelvin. What will be the approximate temperature when the ball of fire expands adiabatically of 1000 meter radius? Okay. Oh, sorry. And this is another. I made a mistake. A certain mass of gas at NTP is expanded to 3 times its volume under adiabatic conditions. Okay, 3 times its volume. That means if V1 you take V, the final volume will be 3V. Okay, expands 3 times under adiabatic conditions. Calculate the resulting temperature and pressure if gamma for the gas is 1.40. Okay, so given at NTP, so that means T1 is given. Okay, at NTP we all know T1 is 273 Kelvin. Okay, so calculate the resulting temperature and pressure if gamma is given 1.4. That means we have to find out T2 and V2. So this is also easy. we know the relation T1 V1 to the power gamma minus 1. This is equals to T2 V2 to the power gamma minus 1. Okay. Now V1 by V2 will be what? To the power gamma minus 1. This is equal to T2 by T1. So V1 is V and V2 is 3V. And you take gamma 1.4 minus 1. And this is T2 by 273. Okay. So this will be simply 1 upon 3 to the power 0.4. This equals to T2 upon 273. Okay. So from which you can calculate T2 176 Kelvin. Okay. So this is the final temperature. You use the relation TV to the power gamma minus 1 to find out the T2. So this is the final temperature. Okay. This is the final temperature 176. Okay. Now you also have to calculate the pressure. Okay. You also have to calculate the final pressure. So you can use this relation P1 V1 to the power gamma. This equals to P2 V2 to the power gamma. Because at NTP we all know P1 is what? 1 atmosphere. 1 atmosphere. This is given. So what will be P2? P2 will be P1 into V1 by V2 to the power gamma. So this is simply 1 and V1 by V2 means 1 by 3 to the power gamma 1.4. Okay, so if you calculate it, the result will become this 0.214 atmosphere. So this is simple numerical. This is also a simple numerical. Okay. Now I follow this numerical from A.B. Gupta and Brijlal's book. Okay. I follow these numericals from A.B. Gupta and Brijlal's book. Okay. There are also various books from which you can collect these numericals. So let us move to numerical 4. 20 gram of hydrogen at 27 degrees Celsius are compressed isothermally to 1/4 of its original volume. Okay, that means if original volume is V, so it is compressed 1/4 times the original volume, that is this. 27 degrees Celsius means it is given 300 Kelvin. Okay. Now 20 gram of hydrogen means, okay, so 20 gram of hydrogen is how much mole? We all know that is 20 by 2, 10 mole. 20 gram of hydrogen means how much mole of hydrogen? That is 20 by 2. Okay, because hydrogen, for hydrogen molecular weight will be 2. Okay, so 20 by 2, 10 mole. Now find the value of work done. So since the gas is compressed, we use a minus sign. And what is the formula? We all know the formula, nRT ln V2 upon V1. So you substitute it. N is 10 and R in which unit we use? SI unit. The value of R is 8.314 joule per mole Kelvin. We use T 300 Kelvin and ln V2 upon V1. So V2 upon V1 will be 1 upon 4. Okay. Okay. So if you calculate it, the result become minus 334.56 into 10 cube joule. Okay. There you see that minus sign comes. And this minus sign is nothing but due to the compression. Since the gas is compressed, a minus sign we get at the result. So it clearly indicates the compression. So this is the formula during adiabatic isothermal compression, nRT ln V2 by V1. All are given, V2 V by 4 and V1 V, T 300 Kelvin. R in SI unit we all know 8.314 joule Kelvin. Okay, and N is given 20 gram of hydrogen means 20 divided by molecular weight, that is 2. 20 by 2, 10 mole. Okay, so this is the amount of work done during isothermal compression. During isothermal compression. Okay, so in today's lecture I do few numericals related to first law of thermodynamics. So in our next class I will do again few numericals related to Carnot engine and second law. Okay, so for numericals you follow these books. For numericals you follow these books, Brijlal, or you can follow CL Aurora. CL Aurora volume 2. Okay, so you can get many numericals in these books and you have to practice it to make your concept clear. Okay, so dear guys, this is all for today. Thank you.